I would like to work through these 4 exercises for this scalar-valued piecewise-defined function. So here we have this function f, which is defined on all of R2 to be the product of x squared plus y squared with sine of 1 over x squared plus y squared whenever x and y are not both 0. And then at the origin in R2, f is 0. This is a pretty famous function, so this is like a classic example of a certain result that we will land on with these 4 questions. So here's what we're going to do. The first thing we're going to do is show that this function is continuous at the origin. If it were not continuous, then we wouldn't have to do any of this, because if it were not continuous, then it wouldn't be differentiable. However, it is continuous. We will work through how to show that. So then we will say, okay, if it's continuous, maybe it's also differentiable at the origin. It's not immediate from looking at this piecewise defined function that it would be. So what we will do is compute the partial derivatives of f with respect to x and y at the origin to construct a proposed Jacobian matrix. We can write down what the Jacobian matrix is before we actually know that the function is differentiable. So this is something special about functions of multiple variables. They can have partial derivatives without being differentiable. Therefore, our ability to do this second step and put together the Jacobian matrix at the origin is not the same thing as differentiability. Then the third question here could be skipped if you went straight to question 4, but I'd like to spend some time with this third question. And that is, the partial derivatives of f with respect to x and y are each also scalar-valued functions of 2 variables. So you could think of them as functions kind of like this one, functions from R2 to R. So we will specify what those functions are, and then we will repeat this continuity computation for those functions. So 1 is kind of a warm-up for 3 here. And then lastly, I would like to wrap up by discussing whether or not this function is differentiable. So we will reach a decision by question 4. All right, our first task is to show that this function is continuous at the origin. What we really want to do here, to rephrase this question, is show that the limit as x and y approach the origin of f of xy, this limit exists and equals the value the function takes at this point. So this is what it would mean to show that this function is continuous at the origin. So let's do that. We need to compute this limit. So when x and y are approaching the origin, they are not at the origin. So whenever you take a limit, you imagine that this is close to here, but it's not actually equal to that, which means that when I look at my function, I know it's this first line that we want to put in for the function away from the origin. Okay, so x squared plus y squared times sine of 1 over x squared plus y squared. You could switch into polar coordinates here if you wanted to. Whenever you see x squared plus y squared, it's pretty natural to want to replace that with r squared, where x is r cosine theta and y is r sine theta. But here you don't actually have to do that. And that is because this piece is always between -1 and 1. So this sinusoidal piece here is bounded. And then x squared plus y squared simply goes to 0 as x and y both go to 0. So this behavior right here is not mysterious. So we have the product of 2 expressions, one of which is going to 0. The other is bounded between -1 and 1. Therefore, we can say that this product goes to 0. And I'm going to think of that as an application of the squeeze theorem. In full detail, what we could say is that this expression is between -1 times this, so negative x squared plus y squared is less than or equal to f of x and y is less than or equal to 1 times x squared plus y squared. So here you really see the squeezing action. This is like setting sine to be -1. This is like setting sine to be 1. So whatever sine actually is, it's between these two bounds on the left and right, and both of those terms go to 0. So overall, this goes to 0. Okay, this computation was not too bad, but we will do another continuity argument when we land on our third question. So just keep in mind that this is the kind of question that we will want to answer for the partial derivatives. Let me step away, and when I come back, we will put together the Jacobian matrix for this function at the origin. Our second task is to compute the partial derivatives of f with respect to x and y at the origin in order to propose a Jacobian matrix for f at the origin before we actually know that f is differentiable. We must use the limit definition of the derivative here. And since the roles of x and y in this function are totally symmetric, if you interchange x and y, you have the same function, we only need to compute one of these partial derivatives. Typically, I do x, so let's do y for variety. We can say the partial derivative of f with respect to y at the origin. Sorry about the nested parentheses if you don't like that. But the partial derivative with respect to y at the origin will be the limit as h goes to 0 of f of perturbed by h in the y-coordinate away from the origin. So that's going to look like f of 0, h, minus f of where we started, all over h. H is going to 0. It's not at 0, which means for this first function value, we're going to look at the first line. So that this will be the limit as h approaches 0 of x is 0, y is h. So we get 0 squared plus h squared times sine of 1 over that. So 1 over 0 squared plus h squared. And then for the second term in the numerator, f is at the origin here. So we know that the function is 0 right at the origin. And then divide by h. Okay, if we look at this expression, okay, we have minus 0, we have 0 squared. So overall, this is h squared sine of 1 over h squared all over h. We can divide the top and bottom by h. And now we're going to do a similar computation to just a moment ago. Sine is bounded between -1 and 1. Anytime you see sines and cosines, keep that in mind. There's certain facts about sine and cosine you should always have handy. And one of them, particularly in limits, is that they are bounded functions. So our sine term here is bounded. H is going to 0. So just like before, the product is going to 0. And again, you could expand on that and show how that's really by the squeeze theorem if you wanted to, but we just did that. So I'll write 0 here, which means, again, using the symmetry of our function, that if f is differentiable at the origin, which we do not yet know, if it is, though, the partial derivatives would both be 0 at the origin. And so this would be the associated Jacobian matrix. I've mentioned this a few times before, but let me say it again. Your ability to compute partial derivatives is not equivalent to differentiability. Differentiability needs a little bit more than just existence of partial derivatives. So what we will do now is finish writing this down, and then I will try to apply a theorem. So in our next computation, we are going to consider the partial derivatives of f with respect to x and y as functions in their own right, and we'll look at what a theorem might tell us. If the theorem is valid, we will know the answer to whether or not f is differentiable. If it's not, we'll have to keep working. The next step is to compute the partial derivatives of this function in general. We know what df dx and df dy both are at the origin. Away from the origin, if I look anywhere else in the xy plane, I can actually just differentiate this using shortcut techniques. Once again, since the variables here are symmetric, let me just work this time with df dx. So whenever we are not at 0, 0, there's no reason in that case to use the limit definition of the partial derivative. So we needed to do that because our function changed definitions at the origin. But just off the origin, this piece here is perfectly differentiable in its own right, so we can just do kind of regular techniques. Okay, probably saying too much. Let's just keep going. df dx as a function of x and y, where x and y are not both 0, is 2x sine of 1 over x squared plus y squared. So that's product rule. I mean, that's the first term in a product rule. And now I'm going to say plus x squared plus y squared times cosine of 1 over x squared plus y squared. I got to do chain rule. So that's going to be -1 comes down, this to the -2 times 2x. So let me write -2x over x squared plus y squared squared. Okay, I think that looks right. We have x squared plus y squared, x squared plus y squared, excuse me. Let's go ahead and cancel that. Which means that I can now write down a general expression for the partial derivative of f with respect to x as a function on all of R2. It's going to be piecewise defined just like this. So let me say df dx in general is 2x sine of 1 over x squared plus y squared minus 2x cosine of 1 over x squared plus y squared times 1 over x squared plus y squared. Let me put it here. Okay, so this is true if x and y are not both 0. And then we know from our previous work that at the origin, it's just 0. So sorry about the formatting here, but this is all one line, and I'm saying 0. Maybe I'll write it here. Okay. Maybe you're writing it a little better on your own paper. But this is now our piecewise defined partial derivative of f with respect to x. It is its own function, and it's a function on all of R2. This is how it's defined in a piecewise manner, just like we had with f. The question we actually want to ask ourselves here is, looking at this piecewise defined function, is this function continuous at the origin? I would like for you to work this out and keep in mind how we assessed continuity for f at the origin in our first exercise. It's the same question here. So is it the case that the limit of this function as x and y approach the origin is the value that this function takes at the origin? The answer is no. Let me explain why out loud, and hopefully it matches what you just did on your own paper. The reason why this function is not continuous at the origin is mainly this piece. As x and y both go to 0, this first piece goes to 0, again by the squeeze theorem. So we have sine, which is bounded, and then 2x is going to 0. So this goes to 0. That looks good. But here, cosine is bounded. That seems okay, but it's this division by x squared plus y squared, which is problematic in this computation. In particular, if you wanted to approach the origin along, say, the x-axis, where y is identically 0, you could kind of ignore this plus y squared. You would be looking at -2 over x as x goes to 0, so that's not going to exist, and overall this limit does not exist as x and y both go to the origin. Since the y partial derivative has the same form, we have the same result for that partial derivative. So I want to make two remarks here. The first is that this example highlights why we must use the limit definition of the derivative when we compute the partial derivatives of this function at the origin. So sometimes I see students want to take the derivative of f, say, with respect to x away from the origin and then plug in the origin, or take the limit as x and y goes to the origin. And that doesn't work because the partials might not be continuous. So you cannot use this expression to get the partial derivative of f with respect to x at the origin. It just doesn't work like that. So that's why you must use the limit definition of the derivative. The second remark I want to make is about more recent results. We proved that if the partials are continuous, so they exist and they are continuous functions in their own right, then the function is differentiable. So if we had said, actually, df dx and df dy are both continuous functions on R2, then we could conclude that this function is differentiable at the origin and its Jacobian matrix is 0, 0. In this situation, the partials exist. This exists everywhere, but it's not continuous at the origin. Therefore, we can't use that theorem. So at this moment, we did a lot of work here, but it's not conclusive. We don't yet know if f is differentiable at the origin. So that will be our final task, is to assess differentiability. For that, we will go back to the grand definition of differentiability and we will compute that limit. We tried the theorem that if the partial derivatives are continuous, you know the function is differentiable. It didn't work. So in order to determine if this function is differentiable at the origin, let's use the definition of differentiability. And as you will see, it's actually just fine. If I were solving this problem from scratch, I probably wouldn't do the third exercise evaluating the partial derivatives. So let's set up the limit that we like to look at when we study differentiability. So that will be the limit as x and y approach the origin. And my numerator for my scalar valued function, that's why I put absolute values, I'm going to look at the difference between f and its first order approximation centered at the origin. So distributing the negative, that looks like f of x and y minus f at the origin minus the Jacobian matrix that we already computed at the origin times the vector x minus 0, y minus 0. Okay, so that's the numerator. And then in the denominator, we're going to take the distance from xy to 0, 0. All right, so that's what we want to do. It's really not that bad because this function we know to be 0 at the origin, and also its Jacobian matrix was a matrix of zeros at the origin. So almost everything disappears from this numerator except for that first term. So I think I can squeeze it here. Let's say, what is the limit as x and y go to 0, 0 of, away from the origin, we have x squared plus y squared times sine of 1 over x squared plus y squared minus 0 minus 0, all over the distance between these 2 points. That's going to be x minus 0 squared plus y minus 0 squared. Could keep going, but let me give you a minute to get to the end yourself. So see if you can evaluate this limit and then reach the conclusion. You probably found that this limit mirrored limits that we've already done a couple times in this video. So wrapping this up, we can say that this is the limit as x and y approach the origin. X squared plus y squared divided by the square root of x squared plus y squared is overall the square root of x squared plus y squared. And then sticking with the absolute values, we would need to enclose the sign in absolute values. Like that. As x and y go to 0, this limit does not exist. I might not have emphasized that earlier because I was so focused on the boundedness, but if you're looking at just this piece, as x and y go to 0, this doesn't go anywhere, but it's always bounded. So it remains the case that our sine piece, actually, because of the absolute values, we could even say 0 and 1. Sine piece is bounded as x and y go to 0, 0. The square root of x squared plus y squared goes to 0. So we have something which is going to 0 times something which is bounded. The product, as we saw earlier, exists and goes to 0. So once again, you could write another line there where you justify that with the squeeze theorem, but we did that for our first exercise, so I think we can leave it here. This is what we wanted to see for differentiability. If f is differentiable at the origin, we need this limit to exist and equal 0. If we gotten 1, then f wouldn't be differentiable. So the fact that the limit exists and is 0 is key. This function is differentiable at the origin, and yet the partial derivatives are not continuous at the origin. It's not even that they're not continuous, but when we looked at df dx and we imagined, say, going in along, I think it was the x-axis, the limit didn't even exist. So we got this kind of strange behavior. So what I would like for you to do is maybe try to picture that for a moment. So what would it look like to say that the partials just are not well behaved as we approach the origin, and yet the function is differentiable? I'm going to step away. We are done at this point with this computation that I have on the board, but I would like to give you some images to wrap up this lesson. The first thing I'm going to do is actually give you the one-dimensional domain analog of this function. I'll label it so you see what I'm talking about. But consider the function f of x equals x squared times sine of 1 over x squared whenever x is not 0, and then it's 0 when x is 0. So that would be a function from R to R, but as you can see, it's It's like the 1D version of this function. I like this function because it's a little clearer to see what's going on. Just the picture is easier because a 2D graph is easier than a 3D graph. From this picture, what you could imagine doing is taking the graph I'm going to show you and revolving it around the y-axis to actually get the graph of this function. So it's like by looking at x squared sine 1 over x squared, it's like we're looking in the slice y equals 0, but this function is rotationally symmetric. So take the 1D picture and revolve it to get the picture of this function. So that's just a mental exercise for you to do. And then I will put up the graph of this surface, and I'll try to give you a few different viewpoints. From far away, as you'll see, it actually doesn't look like anything is really happening. But then when you zoom in and kind of cut away so we can get a good viewpoint, I will show you what it looks like to plot this. But again, you get the full picture of the behavior from just the basic function of one variable. Okay, I hope you enjoyed working through these 4 questions with me and the pictures you're about to see. Thank you for your attention.